So, Samuel, you've given us some concrete examples of RL problems. But how do these different examples actually relate? What's the common thread?
Well, Alfred, the core idea is finding the best actions to take in a given situation, right? Training a dog, investing, or driving, all involve choosing actions based on the environment.
I get that, but the environments seem vastly different. A dog's reaction versus the stock market, that's a huge gap.
Exactly. That's where the power of RL shines. It's adaptable. The training process, the learning process, is adaptable to lots of different situations. You see, the core structure remains the same. You've got an agent, an environment, and a goal.
So the agent is the decision-making part, and the environment is what the agent interacts with. Got it. But actions and observations are pretty important too.
Absolutely. Actions are the possible choices the agent can make to change the environment. And observations are the information the agent receives about the environment's current state. Different problems have different action sets and observation spaces.
Like in the dog training example, actions are talking, waiting, or giving treats, right?
Yes. And observations include the dog's posture, reactions, or even exhaustion. Crucially, the agent learns to map observations to actions that achieve the desired outcome.
So, the stock market example is even more complex. The actions, selling or buying stock, are simple, but the observations, market fluctuations, geopolitical tensions, are significantly more complicated.
Exactly. The environment is much more volatile and unpredictable. That's why advanced RL methods are needed in such intricate environments.
And what about multiple agents? 2 agents in the dog training example? How does RL deal with that?
That's interesting, Alfred. Each agent might have a different goal. The dog wants treats, and you want the dog to sit. Those goals clash. But RL can be adapted to deal with that. It introduces concepts like multi-agent reinforcement learning, where you are trying to coordinate actions, understand the conflicting goals.
So, you're saying the complexity is determined by the environment?
In a way. It's also influenced by the level of abstraction. Dog training is simpler, you know. Driving a car is a step up. It's about balancing complexity with the agent's capacity for learning. That's a key aspect in RL design.
So, Samuel, you're saying reinforcement learning agents have these internal steps? Can you unpack that a bit?
Yeah, every RL agent basically does 3 things. They observe, act, and evaluate.
Observe, act, evaluate. That sounds pretty basic. What does that mean in practice?
Well, imagine a robot learning to walk. It observes the world around it, the floor, the obstacles. Then it acts, takes a step forward. And then, crucially, it evaluates how well that step went. Did it fall? Did it stay upright?
So, it's a feedback loop. That's essential.
Exactly. That's where the learning comes in. The evaluation tells the agent whether its action was good or bad, and it adjusts its future actions accordingly.
This seems like a pretty general description. How does this compare to, say, a simple rule-based system?
In a rule-based system, you program in specific instructions. For example, if you see an obstacle, go around it. In reinforcement learning, the agent figures out those rules on its own by interacting with the environment and getting feedback.
So, the agent doesn't just memorize rules? It actually learns them.
Exactly. This is different. It tries things, gets rewarded or punished, and from there, it learns the best way to behave. It's all about that interaction with the environment.
That's interesting. You mentioned the agent has to learn something. Can you explain a bit more about that?
Absolutely. Learning in reinforcement learning is all about figuring out the best actions to take given the environment. It's not just about memorizing rules, but about finding strategies.
Right. So it's about discovering optimal actions in a dynamic world. This is quite different than simply following preset commands. Why is this process necessary?
Because the world isn't always predictable. Conditions change, circumstances evolve, and a set of rules may not always be sufficient.
It's almost like the agent is building its own understanding of the environment, right?
Precisely. It learns to adapt, to react, and optimize its behavior in response to feedback. That makes it much more flexible and useful for real-world problems.
So, we're basically skipping to the next chapter by moving on from a discussion about how the agent works to how the world it's interacting with is modeled. Makes sense.
Exactly. Modeling the environment is crucial for reinforcement learning.
Okay, Samuel, so you're saying every decision-making problem can be seen as an RL environment? That's a pretty bold statement.
Yeah, pretty much. Think about it. Even choosing your significant other, you're trying to maximize something, be it happiness or compatibility. It's like a trial and error process, right?
Right. But how do you represent that process mathematically?
We use Markov Decision Processes, or MDPs. They model the environment, which is basically everything outside the decision maker.
So, what does the environment actually contain?
Well, it holds all the variables relevant to the problem, everything else influencing the outcome.
Like what?
The stock market's history, a game's current board position, or even your SO's mood. All those factors make up the state space.
State space?
Yep. It's the combination of all possible values those variables can take.
So, the game's position is one state, and another is a different position.
Exactly. And at any given time, the agent observes something from the environment, which is the observation space.
So, is it always the same as the state space?
Not necessarily. The agent might not see everything. Imagine playing chess. You see pieces but not the hidden intentions behind moves.
So, observations are like a filtered view of the actual state.
That's a good way of putting it. Sometimes they're the same, but often the agent only gets a partial view.
Interesting. So, the agent does something, the environment reacts, right?
Precisely. The agent takes an action, and that's the action space. All possible actions in all possible states.
So, the transition function is how the environment changes from one state to another after an action?
That's right. It maps the current state and action to the next state.
And the reward function?
That tells the agent how good or bad the outcome of each action is.
So, essentially, the transition and reward functions describe the environment's model.
Exactly. It's like the rules and feedback loops of the problem.
That all makes sense. So, the RL system tries to learn these functions? Pretty complex.
Yes, very complex. But that's how we model real-world scenarios. By understanding the state, action, transition, and reward functions, we can design agents that are capable of complex decisions.
Okay, Samuel, so this bandit walk environment, what's the deal?
It's a simplified grid world, like a one-row maze. Think of a corridor.
A corridor? So, no branching paths?
Exactly. And it's got a twist. Only 3 states, but only one isn't an ending.
One non-terminal state? Why that?
It's called a bandit environment because it's like a slot machine. You only have one arm to pull. It's a simplified way to explore how an agent learns when only one option matters in a particular scenario.
Ah, so the goal is to find the one good option, right?
Precisely. The agent starts in the middle and can only move left or right. The reward comes when it reaches the right end.
So, the reward structure is pretty straightforward.
Very. +1 for reaching the goal, 0 otherwise. The transitions are deterministic. Moving left means going left.
Deterministic, so no chance of the agent getting stuck, right?
Exactly. That makes it easier to understand the principles. We can also represent it in a table showing states, actions, next states, and probabilities.
A table. Interesting. So, you could quickly see the agent's possible paths and rewards?
Right. It's a really simple way to visualize a reinforcement learning environment. The graphical representation and the table are just different ways to describe the same fundamental setup.
Makes sense. So, why are the terminal states connected to themselves?
That's a good question. It looks redundant, but it helps the transition functions to be complete. If the agent is in a terminal state and takes an action, the environment still needs to specify where it moves to. Since there is no other possible transition, the action itself takes the agent to the same terminal state.
Okay, I get that. So, this is a very simple environment, but teaches us important concepts.
Absolutely. Understanding the bandit walk environment allows us to analyze and build upon more complex learning environments in the future.
Okay, Samuel, so we've got this bandit slippery walk environment. It's stochastic, right? What exactly does that mean?
Yeah, it's a probabilistic environment. Instead of always going where you tell it, there's a chance it'll go the wrong way. Like 20% chance of slipping back.
So, there's uncertainty in the outcome of an action?
Exactly. That's the stochastic part. It's like playing darts, you aim, but there's some randomness to where the dart lands. It's different from a deterministic environment, where actions always lead to the same result.
And how do we represent that slip? Is there a formula?
Not a single formula, but the core idea is in the transition probabilities. We define that 80% of the time, the agent moves forward, and 20% it slips back. That's how we encode the slip.
So, we're not just saying left or right, it's the probability of moving left or right.
Exactly. Each action has a chance of going in different directions.
Okay, I see. So the transition probabilities are crucial here. Are there ways to deal with this probabilistic nature in reinforcement learning?
Absolutely. You need algorithms that can handle the variability. Standard methods for deterministic environments won't work as effectively. We need algorithms built to understand and work with these probabilities.
You mentioned the reward function. Is it the same as before?
Mostly. It's still +1 for reaching the rightmost state, but 0 otherwise, except when it's already in the rightmost state and tries to move again.
Right, important to avoid infinite rewards. And you talked about representing this in a table. What's the point of that?
It's a clear way to lay out the states, actions, possible next states, probabilities, and rewards. That makes it easier to see all the combinations and to program the environment in code. This is super helpful for understanding how the environment will respond.
Interesting. So this stochasticity is crucial?
Absolutely. The real world is rarely perfectly predictable. These models help us learn in environments that have uncertainty. You know, real-world problems often have these kind of complexities. Consider a self-driving car. You can't perfectly predict what other drivers will do.
Right. Or a robot navigating a cluttered room. We need to be aware of these possibilities.
Exactly. The slippery aspect adds a layer of complexity that models must be trained to handle. There are algorithms specifically designed for stochastic environments, which makes reinforcement learning powerful tools to solve this type of problem.
Okay, Samuel. So the environment's not just passively waiting, right? It's actively responding to the agent's actions. Can you elaborate on this?
Yeah, absolutely. The environment's a crucial part of the feedback loop. It observes the agent's chosen action.
So like a game?
Exactly. In a game, the player's action, like moving a character, triggers a response in the game world.
Right, so it's not just press it to win.
No, it's a lot more complex. The environment moves to a new state after that action.
A new internal state?
Exactly. The environment updates itself internally. That's the transition.
Okay. And then what happens?
Then it gives the agent a reward based on that transition. Positive rewards for good actions, negative for bad.
So, the reward is like immediate feedback?
Yup, immediate for the agent. It's the environment's reaction.
But wait, what about this filter? What's that about?
Well, sometimes the actual state of the environment isn't fully revealed. The filter is a process, a kind of simplification. Like, you might not see the precise details of everything happening in the game world at every step.
So, the reward and the new state are sort of filtered?
Exactly. Maybe not all the underlying state details are given, but it's enough for the agent to learn.
Interesting. So, you're saying a crucial aspect of deep reinforcement learning is this feedback from the environment?
Absolutely. The environment shapes the learning process. It gives the agent data to improve its actions.
And is this filtering something you see in real-world applications?
Absolutely. Think about a self-driving car. It can't get every bit of information from the road, but it still gets important info about surroundings, traffic lights, etc., and learns how to drive safely.
So, there's a trade-off between the full complexity of the environment and the information needed for learning.
Precisely. This filter is vital for efficiently training agents in complex environments.
So, Samuel, you were talking about reward signals. They're crucial, right?
Absolutely. They're like the compass for training an agent.
What about dense versus sparse rewards?
Dense rewards give the agent lots of feedback, faster learning, but limit creativity. Think of a game with points for every move.
So like chess?
Exactly. But sparse rewards, less feedback, encourage the agent to explore and find unexpected solutions, maybe even better strategies. It's like a game with a single win reward.
That makes sense. A longer learning process, but possibly greater innovation.
Exactly. Plus, real-world problems aren't always so clear-cut. Sometimes, we have to be patient.
Time steps. What exactly are they?
Think of them as individual actions or experiences within an interaction. It's a unit of time.
So, a millisecond for a fast game, or a day for a complex real-world problem, for example?
Absolutely. It varies hugely. The core is they define a point in time for action and feedback.
And the experience tuple?
That's the record of an entire time step: observation, action, reward, and new observation.
So, it's like a snapshot of the agent's interaction with the environment?
Exactly, a record of the interaction.
Episodic versus continuing tasks? Can you give an example?
Episodic tasks, like a game, have a clear start and end. Continuing tasks, like learning to move forward, don't. Think of self-driving.
So a game ends, the episode ends. A self-driving car doesn't necessarily have an end point.
Exactly. And the return?
The sum of rewards for an episode.
Yeah, the agent wants to maximize the return.
Interesting. So, maximizing return is the fundamental goal in RL.
Precisely. And for continuing tasks, a time step limit creates episodic tasks. It's a way to have a clear goal in a non-ending process.
Now, about policies, models, and value functions. How do they help agents learn?
Policies map observations to actions. Models map observations to future observations and rewards. Value functions estimate future rewards. They're different tools for an agent's learning toolkit.
So, we're taking apart the complex agent-environment interaction to understand the key elements.
Precisely. We break it down to see each part's role.
Makes perfect sense. So, next chapters focus on the environment and the underlying algorithms. It's a gradual approach, isn't it?
Exactly. Building a solid understanding of the environment is crucial before we delve into complex agents.
So, Samuel, we're talking about MDPs now. What exactly are they?
MDPs, or Markov Decision Processes, are models of environments. They describe how these environments work.
Okay, but how do they work in practice? Give me an example.
Imagine a game. The game state, like your current position, influences the actions you can take, and those actions lead to a new state and reward. That's an MDP.
So, an MDP is like a map?
Not exactly. It's more like a set of rules for how things change.
So we build these dictionaries. How do those dictionaries represent the rules?
They specify the possible states, actions, and rewards. Think of it like a recipe for the environment.
So, we're actually creating models? We're not just playing games?
Exactly. We're creating mathematical representations to understand how the environment works. This understanding is crucial for reinforcement learning.
But why do we need these models?
Well, many environments are too complex to understand fully. The rules are hidden. But with MDPs, we can use these models for planning and finding optimal solutions.
So, is this just a theoretical construct? Can we apply it to anything real?
Absolutely. Games, robotics, even traffic optimization. There are lots of practical uses. Plus, sometimes we build an MDP just to check the assumptions on an environment structure.
So, if an environment's dynamics are hidden, how do we even know if our MDP is accurate?
That's a great question. You're right, an inaccurate model can really mess up the whole system. We need careful observation and refinement to make sure our models match the actual environments.
You mentioned something about learning robust behaviors without needing the precise MDP. Explain that.
Even without knowing the exact rules, agents can learn from experience. Imagine a robot learning to walk. It doesn't need a detailed map. It just needs to try things out, learn from successes and failures.
That's fascinating. So, even if we don't know the precise rules, we can use MDPs to guide the learning?
Correct. MDPs give structure and help to shape the learning process, even if those MDPs aren't perfectly correct. That's why they are so important in reinforcement learning.
That's a good point. Thanks, Samuel. Okay, Samuel, so this frozen lake environment, it sounds pretty cool. But what's the catch?
Well, it's a grid world, like before, but with some added twists. It's a 4x4 grid, remember?
Yeah, I'm following.
But the surface is slippery. So, your agent doesn't always go where you want it to go.
So, there's some randomness?
Exactly. There's a 1/3 chance it'll go in the intended direction, and a 1/3 chance it'll go left or right if it was supposed to go up or down, and vice versa. So, it's not a straight path.
That makes it way more complex than the previous environments. So you've got this unpredictable movement. What else?
Yeah, there are also holes. If the agent falls in, the episode ends.
So, a bit like Pac-Man, but with a very slippery surface? Eh?
Precisely. And the reward structure is simple. Reaching the goal gets a +1, and anywhere else is a 0. It's all about getting to the destination without slipping into a hole.
Interesting. So a bigger, more unpredictable grid environment. With these random movements, how is this going to differ from building the MDPs we've already done?
Well, now the action outcomes are not deterministic. This added randomness needs to be represented in the MDP. We'll have to account for these probabilities of going in other directions, in addition to the normal moves.
Right, I get that. We got to incorporate this into the way we define the possible transitions and the rewards. It makes the whole reward and transition function much more nuanced.
Precisely. And this increased complexity, this uncertainty, it's a real-world reflection. Imagine driving a car. There's a similar level of unpredictable forces and constraints.
So, how do we start constructing this MDP in Python? What kind of dictionary structure would this take?
To represent the MDP for the frozen lake in a Python dictionary. It's a little different from the others. We'll have to define the possible states more accurately, which means more than just the states. The possibilities of going where you want, which is not in every case true. The states, the possible actions at each state, and the probability of going to different new states for each of the different actions.
Okay, so the keys might be states, and the values would represent possible actions. Then the values of those values are the probabilities for the next states?
Exactly, and we need to be clear about those probabilities, as you correctly pointed out. We'll have to use those slippery surface probabilities in our calculations.
So, Samuel, you're talking about states in reinforcement learning. Can you give us a simple example?
Sure, Alfred. Imagine a game, like checkers. Each possible arrangement of pieces on the board is a state.
Okay, that makes sense. So, the state space is all possible checkers games?
Exactly. And it's huge. It's not just the current position, but also the history of moves leading to it.
Wait, so a state isn't just about what is, but how we got there?
Exactly. The history is important. The crucial point, though, is that the variables within each state are fixed, not the number of states.
So, the number of variables representing the pieces on the board is the same regardless of the game's progress?
That's right. You always have a finite number of pieces, in fixed positions. The state space is all the possible combinations of those pieces.
So, the number of possible positions in checkers, it's potentially infinite?
Potentially, yes. It's huge, but finite in theory. There are a finite number of pieces, on a finite board. It's just that the total number of ways to arrange those is huge, hence the state space being infinite in practical terms. This is a crucial difference.
Interesting. So, you're saying the size of the state is fixed. It's not the number of states that matters in this case, but the number of possible combinations.
Exactly. And this understanding is very important when designing reinforcement learning algorithms.
So, a crucial takeaway is that even when there's a finite number of variables in each state, the potential states can still be immense, right?
Absolutely. It makes designing efficient algorithms vital. Understanding this state space is key to planning and evaluating optimal strategies in reinforcement learning scenarios.
So, Samuel, you were talking about Markov Decision Processes MDPs. Can you break down what makes an MDP different from a POMDP? and why this matters.
Sure, Alfred. An MDP is like a fully visible environment. You see everything, the internal state. The observations and states are the same. POMPs are more general. You only see observations. They depend on the environment, but you don't see the actual state directly.
So, in a game, an MDP would be like a game with transparent walls, while a POMDP would be like a game with opaque walls.
Precisely. In the environments we've looked at, like BW, BSW, and FL, we're using MDPs. This means our agent knows exactly where it is. It's critical for RL, because most reinforcement learning, RL, and deep reinforcement learning, DRL agents rely on the Markov assumption. The Markov property says the next state depends only on the current state and action, not the whole history. So, if you know the current state and action, you can predict the next state. You don't need the prior states.
Interesting. But in a real-world scenario, like landing a spacecraft, wouldn't the agent need the whole history?
Well, you're right. History might matter in a complex situation. But for the spacecraft, you'd need things like velocities and locations, not just the current position. The agent needs to know these variables to predict the next state accurately and land safely.
So, how do you balance complexity and accuracy?
You add variables, like velocity and acceleration. These give a more complete picture. But more variables mean more data to train the agent. It takes longer, right? And sometimes, even adding location and velocity is enough for simple environments like grid worlds.
Got it. So, in FL, it's just the current cell's ID, right?
Right, just the current cell. It's simpler. In those cases, the Markov assumption works pretty well.
What about these terminal states? What's the significance?
Terminal states are special states. In chess, that's winning, losing, or drawing. The agent needs to understand these and get appropriate rewards. They must transition, with 100% probability, to themselves, with zero reward. It's a convention to allow algorithms to converge to the same solution.
So, in the FL example, 5 states are terminal states?
Yes. And each has a separate terminal state transition. A key thing to remember is starting states and terminal states are defined in the MDP, not the agent's interactions, and the probabilities are fixed throughout training.
So, you have to carefully consider the necessary variables to make the Markov assumption hold true and ensure the right reward system in these environments.
Exactly. It's a careful balance. Too many variables make training slow, too few, and the agent won't learn effectively.
Okay, Samuel. So actions in an MDP are dynamic? They change based on the state?
Exactly, Alfred. It's not a static set of actions. Think of it like a video game. You can't always do everything in every situation. You can't jump if you're on the ground, right?
Right, that makes sense. So, the action set is like a function? It takes the state as input?
Yes, a function as. It tells you what's possible in a given state. It's a key idea in reinforcement learning.
So, you can make actions constant across all states. Like in a really simple game.
Exactly. Or you can make actions state-dependent. Or you could even have actions that are effectively do nothing.
A no-op action. Interesting. So, the action space can be infinite too, not just finite?
Potentially. But the variables within an action must be finite. Think about a robot arm. It might have infinite possible positions, but the individual movements, rotations, translations, are discrete. A step to the right is one action.
So, the number of variables in an action can be different from state to state?
Right. The available actions can change depending on the current state.
That's nuanced. And the environment knows all the possible actions in advance?
Yes, it's crucial. The agent doesn't discover them.
So, agents can choose actions deterministically or stochastically. That's a key difference from how the environment might react, right?
Exactly. The agent decides how it chooses actions. It's either a lookup table, deterministic, or a probability distribution for each state, stochastic. It's all about the agent strategy.
So, in the examples of BW, BSW, and FL, actions are just directions of movement? So, it's really straightforward?
Yeah, Simple directions. 4 actions in FL, up, down, right, left. Each action is a single variable, and the whole action space is fixed in size.
Makes perfect sense. Okay, Samuel, so this frozen lake environment, it sounds like a simplified reinforcement learning scenario. What are these move actions?
Yeah, imagine a very basic 2D world. The agent can only move up, down, left, or right. It's super simplified for teaching purposes.
So, basically for possible actions. And these terminal states?
Right. Those are states where the agent's journey ends. It's like hitting a goal or running into a wall. Crucially, they're defined in a way that makes the transitions predictable.
Deterministic transitions? Can you give us an example?
Sure. If the agent is in a terminal state, there's no action it can take to move out of it, only to stay there, like reaching the end of a game. Crucially, it doesn't lead to an unknown state, just staying put.
So, there are no random elements, just predictable endpoints. So that means no surprises?
Well, no random exploration involved. This is a really stripped-down, teaching environment. It's about showing how reinforcement learning can work, without the chaos of uncertainty.
Why is this simplification useful?
It allows us to focus on the core reinforcement learning algorithm, without being distracted by randomness. It highlights the relationship between actions and rewards, clearly and directly. You get a clearer understanding of how agents learn to reach the terminal state.
Interesting. So, this simplified structure gives us a direct understanding of state transitions. What are the practical implications for complex situations?
Absolutely. Though simplified, it highlights the essential logic. For complex problems, the same basic principles apply, but the possibilities are much more vast.
This is quite enlightening, Samuel. Thank you for explaining these foundational concepts in such a clear and direct way. So, Samuel, you mentioned corner states are special. Can you elaborate?
Yeah, corner states are unique.
Immagine a grid.
Corners have fewer possible moves.
Fewer possible moves? Why?
Because you can't move both horizontally and vertically. You're restricted. This is a key detail, especially for learning agents.
So, bounce back?
Exactly. You bounce back off those walls in the grid. Makes the learning process simpler. The algorithm accounts for that.
Okay. And terminal states?
Terminal states are like end zones. Actions in those states just loop back to themselves.
Why?
Because there's no way to get anywhere else from a terminal state. No new learning needs to happen.
Got it. Stochastic environment?
Very. High chance of unexpected outcomes.
Like how?
Each action has more than one possible path. It's not just the expected outcome. There's a probability for paths in other directions.
That's a complex idea, though. Can you give an example?
Imagine you want to move right. You might end up slightly above or below the intended spot too, right? There's no single path. Probability of each transition affects it.
Interesting. So, you're saying in a frozen lake, even with planned movement, you might end up in a different place. Very unpredictable.
Exactly. That's the whole point. The probability of these unexpected transitions is what makes it so interesting and challenging to learn.
So, Samuel, you were talking about reward functions. They're crucial, right? Tell us more.
Absolutely. Rewards are, well, how we tell the AI what's good. Positive rewards are like a carrot. Negative ones are like a stick.
So, a positive reward pushes the AI toward a desired action, right?
Exactly. Think winning a game or reaching a goal.
And negative rewards
Penalize unwanted behaviors. Like in robotics, time limits mean a penalty for taking too long.
Interesting. How is this reward formalized in code?
It's a function, mathematically. It takes these inputs, the current state, the action taken, and then the resulting next state.
Wait, you can define it with just the current state and the action?
Well, we can do that too, simplifying it a bit. Sometimes, rewarding based just on the state is sufficient. Or just on the action and state. But the most complete way uses a triple: the state, the action, and the next state. This gives us the most information.
So, we have this function that maps these to a number.
A scalar. A single number. Positive or negative, it's all reward. Think of this as an evaluation of that transition.
So, the reward function is dynamic?
Dynamic and contextual. It can depend on different factors in different situations. You can even marginalize the reward, average it over the next state or action. Then you get a reward that reflects the situation.
So, what about the expectation of reward?
That's a key concept. It's essentially the average reward you expect. We consider everything that can happen. This is like calculating the most likely scenario.
Can you illustrate with an example?
Sure. Imagine a robot aiming for a particular location. We can reward it highly for reaching the goal. But if it takes too long or does the wrong action, that's where negative rewards come in.
So, that's the reward function?
Yeah, that's a basic idea. This reward signal drives the learning process. But there are nuances. For instance, sometimes the reward function is stochastic, meaning the reward isn't guaranteed. It's probabilistic. That means some actions have a better chance of getting a reward than others, and the actual outcome varies.
And how does stochasticity complicate things?
The robot might try different paths, a right turn, a left turn, and an upturn from a certain state. Each has a 33.3% chance of success, all leading to the same goal state. All with different actions from the same state leading to the same reward. That's what makes it interesting.
So, Samuel, we've established that time plays a crucial role in MDPs. Can you unpack the idea of a planning horizon in reinforcement learning?
Absolutely. The planning horizon essentially defines the time frame an agent considers when making decisions.
Okay, so like a deadline?
Exactly. Think of it like that. A finite horizon means the agent knows the task ends after a set number of steps. Like completing a puzzle in 15 moves.
In a greedy horizon?
A greedy horizon is a special type of finite horizon where the agent only looks one step ahead. It's really focused on the immediate reward, ignoring potential future gains. Bandit problems are a great example.
Makes sense. But what about an infinite horizon?
An infinite horizon means the agent plans for an unlimited number of steps. It's like planning for a long-term project. That project might still end, but from the agent's perspective, the time to complete it is theoretically infinite.
So, that's an indefinite horizon. So, even though the task might end, the agent isn't aware of a fixed finish line?
Precisely. The agent anticipates interacting with the environment indefinitely. Though, of course, the environment could stop those interactions at any time.
That's tricky. Why would an agent need to plan for an infinite horizon if the task could stop?
Because many real-world tasks aren't definitively timed. For example, training a robot to navigate a warehouse. The work could be stopped any time, or a new part added to the warehouse.
Right, so, how do we deal with agents that get stuck in loops?
We add a hard time step limit. Basically, an artificial terminal state after a certain number of interactions. It's a way to avoid infinite loops. But there are critical details here. How we handle the time step limit termination matters.
So the environment decides the loop is over and the episode finishes, even if the agent hasn't reached a desired goal?
Exactly. And the cart pole environment is a perfect example where this kind of hard limit is needed.
Interesting. So, these episodic tasks like Frozen Lake have a clear start and end.
Yes, with specific goal states. They also tend to have a finite planning horizon.
But Frozen Lake is an indefinite planning horizon from the agent's perspective?
Yes, the agent might plan for an infinite number of steps, but interactions might stop at any time.
Why not just include a time step limit for Frozen Lake?
The environment is highly stochastic, which means it's unpredictable, random. It's much more likely the agent will terminate naturally. We wouldn't want an arbitrary time limit interfering with natural termination.
So, episode, trial, period, or stage, all the same thing essentially?
Well, yeah, they all refer to the sequence of time steps in an episodic task. In an indefinite horizon, it's more specific. It's the set of interactions between the start and ending state.
Great breakdown, Samuel. This makes a lot more sense now. So, Samuel, discounting future rewards. Sounds simple enough. But why is it crucial?
Well, imagine training an AI to navigate a maze. A reward of finding the cheese is good, right?
Absolutely.
But if the cheese is way down the road, the reward's value decreases. The AI might be tempted to take shorter, less desirable paths.
Makes sense. How do we quantify that?
That's where the discount factor comes in. It's like a time value of money concept, but for AI.
So, a smaller discount factor means a bigger future reward impact?
Exactly. A bigger factor, well, means the future gets devalued. A key reason for using it is to stabilize learning. Imagine trying to estimate future outcomes way out in the future. There's a lot of uncertainty.
Right? Lots of room for error.
The discount factor helps reduce that variance by lowering the impact of those uncertain far future rewards.
So it's not just about prioritization, but also about stability?
Precisely. This helps train the AI for long-term planning. Without it, future rewards could become very noisy, leading to poor overall learning.
So what if the discount factor is too high?
Then the future loses too much value. The agent might not consider very long-term rewards at all. Think of an AI looking for immediate gratification only.
And what if it's too low?
The AI will focus too much on distant future rewards, potentially ignoring short-term, more definite gains.
Interesting. So there's a sweet spot?
Precisely. Finding the optimal discount factor often requires experimentation and tuning, depending on the specific task.
Makes sense. So, it's all about finding that balance. Thanks, Samuel. So, Samuel, we're talking about discount factors in reinforcement learning. Can you explain how this discounting actually works?
Yeah, discounting is crucial.
Imagine a reward.
A reward further in the future is worth less than a reward today. That's discounting.
Makes sense. But how is that mathematically represented?
The discount factor, gamma, does that. It's a number between 0 and 1. A higher gamma, like 1, means future rewards are nearly as valuable as immediate ones.
So a 1 means no discounting?
Precisely. A gamma of 0 means future rewards are worthless. Think of it like a savings account. 0 interest, no point waiting.
Got it. So a lower gamma makes future rewards less important, which creates a sense of urgency, right?
Exactly. A lower gamma, like 0.5, means the reward is halved every step into the future. That's urgency built in. For tasks where speed is crucial, this is handy.
So like finishing the book quicker?
Yes. Imagine that $1,000 reward gets smaller and smaller daily. Finishing it now is way more appealing.
Okay, but how does gamma affect the return?
The return, the sum of all rewards, is discounted by the gamma factor for later rewards. It exponentially decays the future reward value.
So a reward later in the episode is worth less in the overall calculation?
Exactly. We're not just adding up all the rewards, we're taking into account how far off they are in the future.
Interesting. Is there a standard gamma value for all RL problems?
No, that's a mistake to assume that. The appropriate value depends on the specific task and environment. Gamma is part of the MDP definition, but is also a hyperparameter. In some tasks, like playing games or something like BW and BSW environments, you might want gamma to be 1.
And in other cases, not?
Yes. You often need to tweak gamma to get the best results. Some environments, like FL environments, often use a gamma of 0.99 because that works pretty well.
So, tuning gamma is also part of the agent's learning process?
Absolutely. It's like tuning any hyperparameter. You might need to try a few values and see which one works best for the specific learning task.
So, different environments will call for different gamma values, you're saying?
Yes, it's completely dependent on the specific environment. A game's complexity, reward structure, even the steps needed to succeed, all impact the most effective discount factor.
Okay, Samuel, we've discussed Markov Decision Processes, MDPs. Now, you mentioned extensions. Can you give us some examples of these extensions?
Sure, Alfred. MDPs are fundamental, but extensions handle more complex RL scenarios. For instance, partially observable Markov Decision Processes, or POMPs, deal with situations where the agent doesn't see the full environment. Think of a robot navigating a room, only seeing parts of it at a time. That's a POMDP.
Interesting. So, the agent doesn't have complete knowledge?
Exactly. It has to make decisions based on incomplete information. Another extension, Factored Markov Decision Processes, FMDPs, represent transition and reward functions more compactly. This is crucial for very large environments.
Compact? Like how?
Well, imagine a huge game with thousands of states. An FMDP finds a way to group similar states and actions, dramatically reducing the size of the representation.
Makes sense. So, more efficient for complex environments. What about continuous variables?
Yes, continuous MDPs are another major extension. Here, time, actions, or states can take on any value. Think of controlling a robot arm in 3D space. The arm's position and movement are continuous variables.
Right. You mentioned a few more types. Relational MDPs?
Relational MDPs combine probability with relational knowledge. This helps if, for example, you want an agent to learn about objects and their relationships in the world. An agent might need to reason about how actions change objects and their relationships in some relational way.
Interesting. That's quite different. Then there are semi-Markov decision processes. Can you describe those?
SMDPs let you include actions that take multiple time steps. Think about planning a multi-stage process. You can have a process that requires several steps, not just one immediate action.
Right, like assembling something in multi-agent Markov decision processes?
Yep. MMDPs handle multiple agents interacting in the same environment. Think of a group of robots working together on a task.
And decentralized MDPs?
Decentralized MDPs are about agents collaborating to maximize a shared reward. These agents might not know the complete state of the environment, but can collaborate effectively. They don't necessarily need to be in the same location, they just need to agree on a common goal.
So, they can potentially solve problems beyond the scope of a single-agent MDP?
Potentially, yes. These are just a few examples. It's a vast field, and there are many more specialized extensions, catering to a wide range of tasks and problem structures.
So what about these specific examples you showed? Like the bandit walk?
The bandit walk is a specific type of MDP environment. Essentially, it's a simplified example, offering a clearer and quicker way for testing and learning different RL algorithms. It's like a controlled experiment in a specific RL environment.
Thanks, Samuel. That was helpful. You've introduced us to some fascinating extensions to MDPs. So, Samuel, we're now getting into the nitty-gritty of MDPs and POMPs. You've mentioned different ways they're defined. Can you explain that a bit?
Yeah, real-world MDPs aren't always neatly packaged. Sometimes, you get just transition functions and reward signals. It's like getting a recipe with only the steps for making something, not the ingredients or instructions about what to do first.
So, we're missing parts?
Exactly. Things like initial state distributions, the discount factor, and the horizon are often hidden. Sometimes, even POMPs are presented as just MDPs.
So, how does that affect us in practical applications?
Well, libraries like OpenAI Gym handle some of those missing parts internally. But you need to understand what's not provided. You know, things are often simplified for presentation.
So, we don't need to worry about those missing bits for this chapter?
For now, just the transition functions and rewards. The other stuff? We'll assume.
Why assume?
For this chapter, focusing on the core principles is key. We'll fill in the details, and I'll give you the discount factors we'll use. We'll assume infinite horizons. Initial distributions? They're not necessary right now. We want to understand what the key components are first.
Okay, so you're saying this is a simplified setup for learning to get the basic concepts across first?
That's right. This lets us focus on the fundamental relationships in MDPs and POMPs, not just the mechanics of calculating everything.
Makes sense. And POMPs? How do they differ?
Just add observation space and an emission probability. That tells us the likelihood of seeing a certain observation given a particular state. Very simple extension.
So, in simple terms, it's like adding another layer of uncertainty.
Exactly. Think of it like, you might see a sign for a restaurant, and a lot of different states might correspond to the same observation.
That's a great analogy. Makes it clearer. Thanks for breaking it down for us. Okay, Samuel, so we've just gotten into Markov decision processes. This is a core concept. Can you give us a simple, real-world example?
Sure, Alfred. Imagine training a robot to navigate a maze.
A maze. That's a good starting point.
Exactly. The robot's environment is the maze itself. The possible positions it can be in are states.
Got it.
The robot's actions are things like move forward, turn left, turn right. Those are actions.
Okay, so we have states and actions.
Right. The transition function shows how the maze changes when the robot takes those actions. For example, moving forward might take the robot from one spot to another in the maze.
So the robot learns how its actions change its position in the maze. And how does reward come in?
The reward signal tells the robot which maze paths lead to the goal, say, a box of cookies. High rewards might be for actions leading directly towards the cookies, and lower rewards for other actions.
So, the robot learns about the maze via rewards?
Exactly. The robot's learning is based on these rewards. It figures out the best way through the maze based on the possible states, actions, and rewards.
So, if the maze changes, the transition function and reward structure need to change, right?
Correct. That's why we say the model is stationary, meaning the probabilities of transitions and rewards don't shift during training. That's key. If the maze changes mid-learning, the robot's learned strategy could be wrong.
That makes perfect sense. What about the horizon and discount factor?
The horizon is like a time limit. If there's no time limit, the robot might keep going forever and not reach the goal. The discount factor is like the value of a cookie now versus a cookie later. If the robot is hungry enough, future rewards could have less value.
So, it's a balance of immediate gratification and potential future gains?
Precisely. The discount factor helps weigh future rewards.
And is the state space always finite?
No, it can be infinite, but the number of variables describing a single state must be finite. So even in a huge maze, the robot's position could be described with a few variables, x-coordinate, y-coordinate, etc.
Interesting. So the robot could figure out a strategy to get cookies, even in a complex, changing environment?
Yes, absolutely. That's the core of reinforcement learning.